Hi, welcome back to Basic Logic and Open Introduction. I think I called it something different every video so far. I'm Dr. Nick McGinnis, and now we are up on Chapter 7 on For All X, the open source textbook we've been using throughout this class. We've been using, of course, the Lorain County remix. Go download the PDF, print it out if you like. In Chapter 6, I introduced the basics of sentential logic, a formal logic system where atomic statements represented by uppercase letters can have one of two truth values, true or false. These are connected by binary connectives, and, or, if and only if, and, of course, a unary negation. Using these, we define truth tables that tell you what happens when you start connecting these things. For example, if I say P and Q, the and is only going to be true when P is true and Q is true and false otherwise. If you want to go back to the videos, I think I made 3 videos for Chapter 6, and maybe I'll make a short summary. But now we're on to Chapter 7, and we're going to be using these truth tables to actually start doing things in our formal system. So we're going to introduce a method by which we can use to kind of test sets of sentences. For what? Well, for various formal properties. I said in the first set of videos covering Chapters 1, 2, and 3 that the most important concept in philosophical logic is validity. Validity is when an argument is such that the truth of the premises guarantees the truth of the conclusion. Alternatively, we could think of it as saying that it's possible to have true premises and a false conclusion. Other properties include equivalence, consistency. Sentences could be a tautology. A set of sentences or a set of sentences could be a contradiction. All these properties of sentences and sets of sentences and arguments can now be proven formally using a number of different methods. The first method we're going to be introducing in this chapter is truth tables. Now, these tests do not actually involve translating sentences to English or any other natural language. We're going to remain perfectly content neutral, which is the way we want it, and only be concerned with the truth values of sentences. Now, we can always interpret a sentence of sentential logic by giving a translation of its variables, the letters. We can set up a correspondence between what he calls the elements of the object language and the elements of some other language. Now, what does that mean? So this is from For All X. Well, the object language is the well-defined formal system, such as SL in our case, which can be interpreted and used. Now, the difference between SL and something like the MIU puzzle is that we assume SL has a meaning to it. The binary truth table represented in AND, we interpret it as being at least close enough to the natural language AND to be useful in translating arguments and determining validity. Validity, of course, being this notion that we can find out whether a conclusion is true on the assumption of the truth of its premises. The meta-language is the language you use to talk about the object language. And in this set of courses, the meta-language is English. For this chapter, I'm going to try to stay content neutral, and whatever semantical interpretation I'm going to bring in is going to focus pretty much exclusively on true, false, and our interpretations of the logical operators. That the AND symbol stands in for AND, that the disjunction is OR, and so on and so forth. Don't worry too much about this. You'll understand what we mean as I go along. So in SL, the truth table gives the full interpretation of a statement, and then the rest is just working out the details. As we've seen in a simple statement, if you connect only two atomic sentences, there's only 4 possibilities. If you look at the middle column here, true, false, 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 this actually exhausts all the possibilities that are there when you're connecting two things that can only have 2 values. But what if I had 3? Every additional atomic sentence doubles the amount of possibilities. So if I had 3, the amount of rows required in the truth table would be 2 to the 3. In other words, I would need 8. Generally speaking, the amount of rows I'll need for a truth table is 2 to the n, where n is the amount of atomic sentences in a statement. So things are going to get a little bit more complicated now. All right, so suppose I have a sentence that goes like this. If P and Q then are, Why did I say if first? Because the main logical operator is the if. So if both P and Q are true, then the consequences are. So in this example, we have 3 atomic sentences, P, Q, and R. So 2 to the 3, 8 rows total. Now, how do we make sure that we cover in our truth table that we created here all combinatorial possibilities? Well, my trick is always the same. Well, it's actually not my trick. I was taught this, and everyone does this. So if you start here with the P, half the rows are going to be true, and half the rows are going to be false. So you go true, 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 false, 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 false. Then you have that again. So if I had 4 trues, 4 false, I'm going to go back and forth, 2 trues, 2 false, 2 trues, 2 falses. Under the Q here. True, true, false, false, true, true, false, false. And finally, for the third one, true, false, true, false, true, false, true, false. So the way to ensure that your truth table is going to cover all the combinatorial possibilities is that the first atomic sentence you choose, typically the one furthest to the left, half the truth table, half the rows are going to be true, the other half are going to be false, and then you have that through every iteration until the last one just goes TF, TF, TF. That's how you know you did it right. So this will work for 4 atomic sentences, 5 atomic sentences, and so on. Of course, the amount of rows doubles every time you add a new atomic sentence. So if I add P, Q, R, and S, then we'd have to do this giant truth table with 16 rows. And then, of course, for the first variable, it would be 8 rows of true, 8 rows of false. Then 4 rows of true, 4 rows of false, and so on until we reach our last variable, which will be true, false, true, false. All right, so that's how you construct a truth table such that all the combinatorial possibilities of truth values for the atomic sentences are there. And once you have those, you always start with the atomic sentences, the values of the operators can be filled out. Now, the main logical operator is always done last. So once I've filled in the possible values for my atomic sentences, which I always do first, P, Q, and R, I can fill in the values for the next operator in line. In this case, it would be the AND. The AND is taking its values from the P and Q. The OR is going to take its values from the AND and the R, so I'm going to want to do that after. So notice here it's true, true, and then false all the way down. Why? True, 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 false, false, and so on. Because the AND is only true in one case, when both of the things it's connecting are true. Then I'm going to take this AND, this column here, and combine it with the values of the R using the if truth table. This seems a little complicated, but remember that the truth table gives the full definition for all possibilities already. So P and Q is really just a you can think about it as a metavariable, and the values of that metavariable are given by the main logical operator of this subcomponent. So the value of the AND, because it's a binary connective, the value of the AND and the value of the R is what is going to give you the values of the if then, using the guidelines of the original if P then Q truth table. Right? What is the if P then Q truth table? It's true, except in one case, when the antecedent is true, but the consequent false. So true, false, false, true otherwise. True, 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 false, 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 true, true, false, true, true, false, true, true, false, 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 true, true, true. So in every case where the antecedent of a conditional is false, the conditional itself is true. So you see that big row of false down here? You know that this is going to be a big a big column of false down here. That's going to make a big column of true down here. So that's how you would build a more complicated 3-valued truth table. Remember, apart from the negation, all the sentential connectives are binary. They're always going to take 2 inputs, and those 2 inputs will tell you the value of the connective itself. So no matter how complicated a sentence gets, you can always break it down into its component parts, knowing that the connectives are going to take binary inputs. And the binary inputs, what you do with them is told, you know because you have the truth table already. And the binary truth table that we've given you in the previous videos for Chapter 6 is all the information you need to have to determine what the rows of the column here is below the main logical operator. So again, it's important to remember that the value of an individual atomic sentence is always going to be kind of the fundamental unit of the truth table. It should be consistent across a single row. Atomic sentences are true or false, but they can't be both. And the size of the truth table is going to be determined entirely by the amount of atomic sentences, even very long sentences. So in my last example, we have 3 atomic sentences. 3 atomic sentences mean we had 8 rows of a truth table. But if I only have 1 atomic sentence, I only need 2 rows, even if I have a very long sentence, something that looks like this. Right? So here the main logical operator is the AND, so we have like if C, if and only if C, then C, and not the case that if C, then C. What the heck does that even mean? Well, it's a weird contradictory sentence, but it's syntactical. And if you look at underneath the main logical operator, it's a sentence that's always false. So it's a contradictory sentence. I'm kind of foreshadowing what we're going to be doing later here. So even a very long-looking sentence doesn't have a long truth table if it doesn't have many atomic sentences. Because it's the amount of atomic sentences, uppercase alphabet letters, right, that will determine how big their truth table is. So if I have 1 atomic sentence, I'm going to have a 2-row truth table. If I have 2 atomic sentences, I'm going to have 4. If I have 3 atomic sentences, I'm going to have 8. If I have 4 atomic sentences, I'm going to have 16, 32, 64, 128. But I'm never going to ask you to do a 128-row truth table. That's too big, and that's what we have computers for. Okay. But when you're completing a truth table for a long sentence like this, you have to remember kind of the order of operations here. The last column to fill out, as I've been stressing, is the main logical operator. It takes as input everything else that it connects, so you have to break things down to their subcomponents. So what do we do first? I have a little row here of numbers. 1 represents the thing we do first. We do the atomic sentences first. What do we do next? We do what the atomic sentences are connected by. Number 2 here is the if and only if and the if. Then, next I do the if here and the negation there. That's number 3. Step 4, when we're done, is the main logical operator. The main logical operator is going to take its values from the values of the previous step. So the values under column 3 and 3 here. All right, so it's an AND, so true, false, 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 false. So this sentence is always false. In other words, it's a contradiction. I said this was a little bit of foreshadowing because roughly if you use a truth sentence, if you use a truth table to verify the properties of a sentence, you'll find that you can determine a property like whether something's a contradiction by looking at the values of the column underneath the main logical operator. If the column is entirely F for all false, then there's no case where the sentence is true. If there's no case where the sentence is true, it's a contradiction. So, this is basically how we're going to be using truth tables to prove things about sentences in sentential logic, or sets of sentences. So we had tautologies, contradictions, logically equivalent sentences, consistent sentences, and valid arguments. So what we're basically going to do here is that we're going to use truth tables to verify these properties. Now, a tautology is a sentence that's always true. So what we would expect is that underneath the main logical operator, we'd have a nice column of always true. T, 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 T. A contradiction, we just looked at one, is a sentence that's always false. Using a truth table, we'd find that the main logical operator has a column of F's. Equivalence, well, we do the truth tables for both and we find out that they have the same truth values underneath their main logical operator. Or if we want to be a little bit more formal about it, we could create a biconditional where sentence 1 and sentence 2 are combined with the biconditional as the main logical operator, and their biconditional is a tautology. We have a nice column of T's underneath the biconditional operator. That means they're equivalent. Sentences are consistent. If there's one truth value assignment where all sentences are true. So the way I would do that is to put the sentences next to each other and find at least one row where all the sentences in them are true. That's a bit less clear, but we'll do some examples. And finally, validity, I could find an argument in SL would be valid if there's no assignment where the premises are true as the conclusion is false. So I would do the truth tables and look for the row where all the premises are true and check to see if on that row the conclusion is false or not. And if there's no such row, then the argument is valid. So we're going to do examples of all these. So let's start with tautology. A tautology is a statement that is true just as a matter, as it were, of logic, because it can't be false. Earlier I gave an example in English, either it is raining or it is not raining. I'm never going to be wrong. Either it's raining or it's not. We can use truth table to determine whether a statement is a tautology. Not an English statement necessarily. The English statement might be represented by a sentence of sentential logic. But for the purposes here, imagine we're testing whether or not a sentence of SL itself is a tautology. So, as I've said, we should expect that the column underneath the main logical operator only has T's. This kind of means that the tautology is not sensitive to any kind of variation in the world. If the rows of the truth table represent ways things could be, the tautology always responds, yep, those are all the ways things could be, and I'm still true. So if it's raining or it's not raining, if I look outside, it's raining, either it's raining or it's not raining, it's true. It's not raining, either it's raining or it's not raining, still true. So the tautology doesn't care the way the world is. So here's an example of a tautology. If P, then either Q or P. So what do we check? We check the column underneath the main logical operator. True, 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 true. So this is truth functionally true, a tautology. Why is this a tautology? Roughly because there's no case where, right, what would be the falsification condition of a conditional, where the antecedent here is true, but the consequent is false. Is there such a row? True, 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 true. If you want to think about it informally, now the best test is, of course, to use the full truth table, because if you do it right, you can't be led astray. But if you think about it a little bit, it makes sense that if P, then either Q or P is a tautology, because roughly it reduces to if P, then P. The only case where it could be false is, well, let's do it on the board. Let me erase some stuff here from the last video. I find the erasing to be the most exciting part of a YouTube video. So my sentence is, if P, then either Q is true or P is true. Now, can this sentence be false? So why don't I just start by actually putting a big false underneath the main logical operator as kind of a hypothesis, question mark. Can this be false? It's kind of an informal reason. The truth table check is what we're doing right now. But in order for this to be false, how is a conditional false? A conditional is only false in one case, when the antecedent is true, but the consequent, this part, is false. Does this mean Q is false? P is false? No, it means that the disjunction is false. So that's what we want. We want true, false, for this to be false here. All right. So how is a disjunction false? A disjunction is false when both sides are. So I'm going to want to see this value here, this value here. False, false, false. Now we have a problem. What's that problem? P is supposed to have two values that are different at the same time. P is false, but also P is true here by hypothesis. That's a contradiction. That doesn't make any sense. So the case that would make this sentence false involves P having two values simultaneously, true and false. But sentences can be both true and false. They can only be either true or false, exclusively. Wait, bivalence is an exclusive or? Yeah. Go read up about pair-consistent logic if you're interested in this issue. But roughly, the assumption that this sentence is false leads to a contradiction, which is more or less what you'd expect, because it kind of reduces to the sentence, if P, then P. And that's definitely a tautology. If P is true, then P is true. Yeah. If you're not sure about this, what should we do? Well, we should do the truth table, the full truth table check. If P, then P sounds like it makes sense as a tautology. How are we sure? Well, P can either be true or false. P can either be true or false. Now, it would be a mistake to do something like this, by the way, right? False, true, because it's the same atomic sentence. So on individual rows, it should always have the same values because it's the same thing. True, false, false. That's a mistake, right? Oh, it's false. No, no, no. The problem is you didn't maintain consistency of your truth values, right? So this is the same P, so it's going to have the same value. So true, 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 false, false, true, right? Because, right, the truth table for if then says that it's only false in one case when true, false, but there's no such case, so if P then P is another tautology. How do I know it's a tautology? I look underneath the main logical operator here, and I see a column of T's. So informally, it makes sense that this one's a tautology, and if I do the full truth table, I see that underneath the main logical operator, there's only T's. So if P then P is true as a matter of logic. It can't be false. If it's raining, then it's raining. That's a tautology. What about contradictions? Well, a contradiction is always false, no matter the values of its atomic sentences take. So it's kind of the opposite of a tautology. So our definition here, which I'm calling a semantic definition because it's based on the truth tables, is simply the converse of a tautology. It only has F's underneath its main logical operator. So there's the example we looked at earlier, the long sentence using only one atomic sentence C was a contradiction. Here's another. If P then Q, and not the case that either not P or Q. Now not P or Q is logically equivalent to if P then Q, so its negation conjuncted with the conditional is probably going to be false, which it is here. So you look underneath the main logical operator, we have a nice column of F's, which means that this sentence is a contradiction. You can't say if P then Q and then say not the case that either not P or Q. This is one slightly more complicated, but you could pause the video, have a look at that truth table, and see if it kind of makes sense. Did he work out the values there? Right, we see that here's the regular if P then Q truth table, true, false, true, true. This is going to be the inputs to the AND. The other input to the AND will be the negation here. Where is that negation getting its input from? The next logical operator in line. Is it this other negation? No, it's the OR. So true, false, true, true becomes flipped to false, true, false, false. So this if and this negation and an AND goes true, false, 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 true, false, true, false, false, true, false, false. Because an AND is only true when both sides are true. So this statement is a contradiction. Let's do a slightly easier contradiction. How about P and not P and Q, say. Now, is this a contradiction? Sure it is. Why? Because we have P and not P, roughly. So, suppose, should we do the full truth table? We can do a shortened one as well. The shortened truth table technique is pretty easy. And I've already done it once before. Roughly, it involves, what did I do last time? I assumed the opposite of the conclusion and derived a contradiction. So we're asking, is this a contradiction? Yeah. How do I show that it's a contradiction? I show that there's no case where it can be true. So I'm asking a question. It's my hypothesis. Is this sentence true? Well, what does it need to be true? It needs to be true on both sides, right? So this over here, and then this is the kind of secondary logical operator here. So this has to be true. What's the case when this sentence is true? That both sides are true. All right. So then this negation has to be true. So P has to be false for not P to be true. So false, true. So if the value of P is false and the value of P is true. So in order for this sentence to be true, one of its atomic sentences have to be simultaneously true and false. That's an impossible situation. That's a contradiction. So the sentence can't possibly be true. It's a contradiction. We can do the full one pretty easily. Let's do a full truth table quickly. So we have two atomic sentences, so we're going to need 4 rows. True, true, false, false. True, true, false, false. I did it again because P, this is the same atomic sentence, right? So P and P, they're always going to have, if an atomic sentence reoccurs later in a sentence, it's going to have the same values as its other occurrences. That's really important to remember so you don't make a mistake. Now Q here is going to be true, false, false. And this is all the possibilities of P and Q together. What are we going to do next? What's the next one in line? It's not this one. This is the main logical operator. It's going to go last. Is it this one? No, it's not, because we want to do the not, because the and is going to take its value from not P and Q. So we're going to want to flip these values to false, false, true, true. Now we can do the and. And is only true when both sides are true, so I want to go false, true, false, false, false. Right? False, true, false, 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 true, 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 false, false. That makes sense? Now, this one here and this one here is going to combine together to give you the values of the main logical operator. And if I did do it right, it should all come out to F's, giving us the contradiction. So true, hooray, false, boo, true, false, 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 false. So under every possible truth value assignment, the sentence's main logical operator comes out false, so it is, as we expected, a contradiction. So you can use the truth table to prove that things are tautologies or contradictions. So the simplest contradiction, of course, you can express is simply P and, not the case that P. It's a core assumption of classical logic, of course, that things can be both true and false. This is the principle of non-contradiction. Sometimes this actually gets you into problems, because in languages that are more expressive than sentential logic, there are paradoxes of self-reference, such as saying, this statement is false. This statement in false is actually really difficult to get a handle on, because it's saying of itself that it's false. So it's not saying something that's true. But if this statement is false, then it's in fact true. So it's true that this statement is false. But if it's true that it's false, then it's saying of itself something that's true, namely that it itself is false. So, oh gosh. You see what I mean? This statement is false is a big problem. So how to avoid and deal with these paradoxes is a bit of an ongoing controversy in formal logic. I say ongoing even though most people think we could just kind of stipulate that self-reference is not allowed in a system. Some other people, like Graham Priest, have developed paraconsistent logics, which say that you can have true contradictions. It's just kind of you can think of it as a third value. Instead of true, you have true, false, and both. Other people don't like that because, well, it just doesn't sound, it sounds like you're dealing with the problem by stipulating that it's no longer a problem. If you're interested in it, just Google paraconsistent logics, logics of contradiction, or Graham Priest. There's a lot of great literature there. Now, there are a number of other paradoxes, of course, in logic. The sentential logic is not really fully expressive enough to give rise to them by itself without kind of importing them through a translation of natural language sentential logic. But here's some other fun examples. If I tell a robot, if this sentence is true, you'll do what I say. You can work out why that's kind of paradoxical. It has to do with the truth table of the conditional. Right? Well, roughly the sentence is either true or false. If it's true, then the antecedent is true. But if the sentence is true, the antecedent is true, the consequent must be false. Let's say the sentence is false. Then the antecedent must be false also, because this sentence is true. It's false. Conditionals with the false antecedent are always true, so the sentence can't be false because of contradiction, so the statement must be true, the robot must do as you say. Yeah, put that in your pipe and smoke it, Elon Musk. If I ask you to self-destruct, would the answer to be the same as the answer to this question? That's great. Genius. Okay. Now we're going into half an hour. I think I'm going to stop here. I'm going to take a break. And then the next video, we're going to talk about contingent sentences, consistent sentences, and maybe we're going to get to validity. All right. Thanks for watching.